Hello, and a very warm welcome to today's Nucleic Acid Insights webinar titled Elevate LNP Optimization with Sunshine and Stunner. I'm Casey Nevins, an editor at BioInsights, and joining me today is Kevin Lance, who will discuss how Sunshine and Stunner streamline LNP optimization and production by offering flexible process conditions, rapid analysis, and efficient detection of aggregates, saving time and resources in LNP development. After the presentation, we'll have a live Q&A session. We invite our audience to pose their questions to our speaker using the Ask a Question box at the bottom of your screen, and we'll try to get to it during the session. I'd also like to draw your attention to the Resources tab on the right-hand side of the screen, where you can find more information on the topics covered today. Now I'd like to introduce our presenter. Kevin Lance, a global expert at Unchained Labs, specializes in biophysical characterization of biomolecules. He earned his PhD in bioengineering from the UC Berkeley UCSF program. Now, without further ado, I will hand you over to Kevin to kick us off with his presentation.
Thanks for the introduction. I'm excited to tell the story of how the combination of Sunshine and Stunner make for a perfect pairing for optimizing LNP workflows, buffers, and storage conditions. Allow me to introduce you to the ladders. They're a part of hiking around Mont Blanc in Switzerland. I got to do this hike recently, and I thought they are a great analogy for a good LNP optimization process, right? The ladders speed things up, they're robust to withstand thousands of hikers per year, and they're easy enough everyone knows how to use them. And the stakes are pretty high for failure. And yes, that's a pretty representative picture of my reaction to them. I did not know about the ladders until I had to climb them. But back to LNPs. When working with LNPs, optimizing your process and flow parameters can be a tough nut to crack, and when scaling up, you don't want to change anything and be stuck with more optimization. All that optimization is going to require a careful balance of producing LNPs under different conditions, while also producing enough of them for your characterization tools. In this seminar, we'll show you how Sunshine and Stunner make for the perfect pair for accelerating LNP optimization and development in a robust way that holds up to the demands of scale-up, and they're both easy enough to use to get where you need to go. We'll compare multiple LNP formulations, flow rates, and cryoprotectant buffer conditions to see how size, polydispersity, aggregation, and total RNA concentration stack up after production and after freeze-thaw cycling. So first, let me introduce you to Stunner. Stunner is all about nailing down nanoparticle quality by checking size and polydispersity from your LNP sample, particle concentration or particle titer, if there's aggregation present, and what the total concentration of RNA is that's present in a sample. So without skipping a beat, you'll know if your nanoparticle is good to go by checking everything about size, concentration, titer, aggregation all at once. Stunner does this by using a 96 format plate where each well has been replaced by a microfluidic circuit. Inside of that microfluidic circuit, Stunner is able to gather both UV-Vis information that's going to be used to determine RNA concentration and gather DLS or dynamic light scattering data that's designed to work perfectly with larger particles like LNPs are. Each of these microfluidic circuits is designed to work with 2 microliters of sample. So all you do is pipette in 2 microliters of sample, and Stunner does the rest of the work to get that RNA concentration data from UV-Vis and the right kind of fit-for-purpose dynamic light scattering data for sizing. Here we can see exactly what sample loading looks like with the help of some fluorescein and a black light. In 2 wells, we've already added our 2 microliters of fluorescein. As you can see, to load another sample, you simply add in 2 microliters into that input well, and the sample wicks into the plate through capillary action. That was shown in real time there, so you can see that it was super simple and quick with a minimum of prep. This is also compatible with multi-channel pipettes too for when you really get into high throughput. Here's the basic problem that needs solving in the world of DLS. Antibodies and LNPs are vastly different sizes. They don't behave the same way when they interact with laser light. You need different applications for different molecules, since one approach to DLS doesn't fit perfectly for every size molecule. In other words, you should be using fit-for-purpose DLS that's going to be a little bit different in its parameters when you're looking at a small, relatively small, 10 nanometer antibody sample or a larger 80 nanometer LNP sample. So when you gather fit-for-purpose DLS data on Stunner, it's going to give you all the DLS results you need, which with the z-average, hydrodynamic diameter, and PDI, but also an intensity, mass, and number weighted size distributions that have a quantifiable area under the curve. So however you're reading your LNP, you understand the average size, you understand the intensity of all the different populations that are present, how much is there relative to the mass, and how much is there relative to the number of particles. Stunner allows you to do this for up to 96 samples at a time because it's using that normal 8x12 96 sample format. So you can keep up with LNP sizing data as fast as you can make them, or actually run as many replicates as you want. Now let's dive into why DLS angle matters for LNPs. For small things like antibodies, they will typically scatter light evenly in all directions. So angle doesn't matter, and doing DLS with one angle is fine for antibodies. So what you can see here is 7 different angles measured on Stunner, and the z-average size doesn't really vary across them. And conceptually, this is because the light is being scattered evenly in all directions when your particles are small enough, which is what the criteria that antibodies fulfills for us. However, for larger things like LNPs, the story about the DLS measurement angle gets more interesting. When LNPs are all the same size, everything actually will look very consistent across the angles. So now we're reading a larger LNP sample. This one's actually very homogeneous in size, and across the 7 different measuring angles of Stunner, we see a consistent z-average size. However, when aggregates are present, light scatters differently at different angles. So forward angles, here and here, pick up on aggregates first, while backscatter angles, here or here, don't see aggregates as well. This is important because a lot of DLS instruments are limited to only measure z-average size at backscatter angles. Stunner, however, allows you to track size across many angles and see if you have a consistent size or if aggregates are mixed in. So if the challenge is that angle matters a lot when you're measuring DLS on larger particles, Stunner solves that challenge by taking a single DLS detector and rotating it through multiple angles. This gathered data, typically at 7 angles, to get enough info to handle larger particles properly. We call it rotating angle dynamic light scattering, or RADLS, and here's what it looks like as the detector rotates around to different angles. To prove the benefits of looking at different angles by DLS, we're going to run a spike-in study. We'll take a good LNP sample of about 80 nanometers in diameter. That's going to be nice and homogeneous. And we'll add in an aggregated LNP sample that's much larger, much more heterogeneous. We'll add small volumes of that large aggregated sample into the good sample and see what we measure by DLS. First, we want to characterize each of those samples, of course. So here we have the good sample with an average z-average diameter at 0 degrees of about 78.9 nanometers, of PDI of less than 0.1, and very nice sharp distributions by intensity and mass in green and blue respectively. Our aggregated sample has a much larger z-average, much larger PDI, and you can see how there's lots of aggregates present in the distribution. To analyze these mixed samples, we're going to compare z-average at 0 degrees, which is the extrapolation of all the DLS info that Stunner has, to the 0 degree scattering angle. That gives you one clear output that is angle independent, meaning you have the best ability to look at the average size of all your particles in solution and not miss a large particle because of the angle you look at. We'll compare that z-average at 0 degrees to the z-average that you would get from a backscatter angle. Those are the angles nearest to 180 degrees, where the laser basically bounces back out towards itself. Those angles are most likely to miss aggregation. If we take a look at our spike-in study, and we're looking at those backscatter angles, as we add more and more of the aggregated LNP to our sample, backscatter z-average DLS doesn't actually see any change in size. Likewise for PDI, so there's no discernible difference between any of these samples. However, if we look at Z average at 0 degrees, we can see a very clear trend as we add more and more of the aggregated LNP sample into our nice happy LNP sample, our good LNP sample. We see a significant visible increase in Z average at 0 degrees and an increase from 78 nanometers all the way up to 244 nanometers. That was completely missed by only looking at backscattered DLS angles. So I've already mentioned that size and particle concentration are critical components to measure. And here we can actually take all that DLS information that we're gathering and plot it in two ways. One is as a distribution of size versus particle concentration. So here we have a smaller LNP in green and a larger LNP in blue. And we can also convert that to a raw particle per mil concentration or titer and understand how many particles are present in our sample. So in this case, it becomes clear that for these samples, we have almost a tenfold higher concentration of LNPs in the small LNP sample than in the large LNP sample. So that's characterization of LNPs on Stunner. Now it's time to think about production of LNPs with Sunshine. Sunshine is going to enable us to take our set of lipid formulations and our sets of buffers and produce them in an automated way where we can get through 10 experiments in 15 minutes in a volume that makes sense for optimization and development, as low as 1 milliliter all the way up to continuous flow. So that means that we can prove production consistency and run our storage and freeze-thaw experiments on the different conditions that we want to test out. It's also doing this with reusable microfluidics so that we can keep using the same chips in all the different experiments that we're mixing LNPs in. Okay, so first thing we're going to do is evaluate which total flow rate or TFR we want to use. So in this case, we're using a Sunny X chip with a 100 micron diameter junction and cross-type mixing, and we're evaluating 5 different flow rates from 2 mil per minute up to 10 mil per minute and seeing how the size of LNPs responds. So you can see that in the graph that anything above 4 milliliter per minute, you start to plateau around 80 nanometers in diameter. The formulation that we're using here is based on the SM102 formulation from Moderna Spikevax, and we're going to actually pick from this experiment 8 milliliter per minute TFR for further lipid and buffer screening. Okay, so now we're going to get into our experiment. So in this case, we have 3 different lipid formulations. The standard one based off of Moderna Spikevax, one always shown in blue, that's going to be our DOPE formulation, where we've swapped out the structural lipid DSPC for DOPE, and one always shown in gray, the ALK 0159 formulation, where we've changed DMG PEG 2000 to an ALK 0159. We'll be evaluating these 3 different lipid formulations against 8 different buffer conditions: PBS, tris, and tris with sucrose, tris with mannitol, where each of those sugars has been added at 3 different concentrations. But first, when we're adding sugars at different concentrations into our formulations, viscosity is something we need to keep an eye out for. Viscosity is a necessary input in DLS, and you need the correct viscosity to read the correct size. So to read viscosity data, we're going to rely on Honeybun. Honeybun is our rapid viscosity system built to get data as fast as you need it, taking it up to 10 samples at a time and delivering data in as little as a minute for samples up to 150 centipoise. When we run our buffer conditions on Honeybun, we're able to quickly understand the viscosity impact that all these different sugar concentrations make. So in our tris plus sucrose formulation, we can see, looking across the green bars, how adding increasing concentrations of sucrose or adding increasing concentrations of mannitol increases viscosity, as you'd expect. And then we also evaluated 3 different temperatures, so you can see how at increasing temperatures, viscosity also drops. All this data was gathered within 10 minutes on Honeybun, since it's designed to give you results rapidly. Once we know the viscosity of our different buffer formulations, we can then apply it to our DLS information to go from an uncorrected size value shown on the left, where applying an incorrect viscosity value can lead to differences in size, in our case as large as 20 nanometers. But once we correct for the appropriate buffer viscosity, you can see that across these conditions, our LNP samples are actually quite similar in size. Okay, so now we're going to first start to evaluate what our different lipid formulations, so our standard formulation, our DOPE, and our ALK 0159 formulation, how they behave in our 8 different buffers. So here we have standard PBS, tris after buffer exchange, and tris with the addition of 3 concentrations of 2 different kinds of sugars. So if we're looking only at backscattered DLS, which again is the angle closest to 180 degrees, which is conceptually backwards towards the laser, what we're going to see is maybe relatively consistent sizing. There's not an extreme trend that I'm seeing here going across all the different samples. However, if we then use Stunner's full angular capabilities and use rattles to understand the z-average diameter at 0 degrees, so we're gathering 7 different angles of DLS data and extrapolating back to the 0 degree angle, we can see a clear story where it's starting to be apparent that the DOPE formulation has much larger z-average size that these exact same samples did not see by pure backscattered DLS. So that's the first note that we're going to see. Is that anything that's not in PBS and has DOPE lipids start to be highly aggregated with z-average diameters at 0 degrees, anywhere from 119 to 244 nanometers. If we take a look at that by actually checking out the rattles distribution graphs from Stunner, the intensity weighted distribution clearly shows the presence of aggregates in the DOPE sample right there. So that's what intensity distribution graphs are excellent at, is understanding the presence of rare, large populations. So they show up very nicely on that intensity graph. And the mass distribution shown in blue tells a more nuanced story with a mass diameter here of about 66 nanometers. So that's our main peak population. But then we see the aggregate population is still present here. And it gives us an understanding of how much aggregates are actually present in that sample. So that's an illustration of why the angle you use matters. In short, it's the average diameter at 0 degrees that takes into account all of the DLS information gathered by Stunner at lots of different angles, gives you a clear picture when aggregates are present, while backscattered z-average diameter can miss that. Next, let's pivot to quantification. Typically, when you're thinking about quantification and want to go as fast and as simple as possible, you go to UV-Vis. But nanoparticle solutions are typically so turbid and cloudy that they block most of the light, so traditional UV-Vis approaches fail. Thankfully, Stunner has a few tricks up its sleeve. Here we're seeing an LNP sample in Stunner's cuvettes. So to read the plate, Stunner pumps the sample into our 2 fixed microcuvettes, which have path lengths of 0.1 and 0.7 millimeters. And because of these short path lengths, light can still pass through and enable absorbance measurement. So we're actually looking at an LNP sample, but able to see through it because of those short path lengths, just like Stunner will see through it. When you read those cloudy solutions of LNPs on Stunner, what you get looks a little bit like this. On the left, we have the raw data, where you can see the predominant sort of decaying signal. That's actually what turbidity looks like by absorbance. This little shoulder at about 260 nanometers, that's going to be an RNA signal. If you're just dealing with raw signal by UV-Vis, that can be hard to deal with. So Stunner has unmixed algorithms that deconvolute that absorbance signal into its component parts. On the right, you can see the black line, which is the total spectrum, the gray, which is the turbidity that's now been deconvoluted out, and the remaining absorbance goes to RNA in green and lipids and buffers in blue. So this green spectrum will be what's used to quantify the total amount of RNA present in a sample. And when we do this across a whole plate of LNP samples on Stunner, we see amazing precision. So in this case, it's a single LNP sample run in 96 replicates with a percent CV of about 1.54%. If we use this against our samples of 3 lipid formulations and 8 buffers, we can quickly track concentration of our poly A in our sample. And in this case, we're mostly going to use this to track concentration after dialysis as we go from one buffer to another, so that we understand where, osmotically there was a change in how much LNP samples that we have present. And we'll just note in this experiment, they have lower concentrations present in PBS and tris, And this could be all just an impact of osmotic potential differences in those buffers during dialysis, and that could all change the sample volume. Okay, so next we want to actually study the final, let's say, use case that we were trying to get to in this experiment, which is evaluating those 3 lipids and those 8 buffers against storage conditions. So first we'll check out 4 degrees C storage first. Once again, I think the story here is pretty consistent, but we'll look at Z-average backscatter, and we see in a couple of conditions we have DOPE samples with higher diameters, but generally the story is across all these samples, Z-average backscatter appears consistent between about 60 and 80 nanometers. But if we turn the page and again look at Z-average diameter to get a more sensitive read on aggregation present in our sample, we can see the clear aggregation winners and losers, with standard lipid formulations being the most stable, typically less than 100 nanometers by Z-average, and all with PDIs of 0.1 or below, while the other formulations start to increase in diameter. If we then compare our little DOE against a freeze-thaw experiment, where we're taking the samples down to -20 C and bringing them back up. Once again, the story for Z-average backscatter is that we don't really have an ability to differentiate a lot of samples. We can kind of make a rule of thumb that sucrose is better, but a lot of samples look very similar across the spectrum of samples that we're running. But when we look at Z-average at 0 degrees to check out the ability of detecting every single aggregate present in our sample, we see that Z-average 0 degrees shows that tris and PBS have higher levels of aggregation, and we can see a trend across the data where the standard lipid formulation is going to be generally better than the other 2 lipid formulations. We can also see that, generally sucrose is a better formulation buffer. We'll take a look at that a little bit more quantitatively in the next slide. Okay, so if we use a little bit of statistics, we can quickly check out the winner by summarizing this data. So across the 3 different lipid formulations, the standard lipid formulation has the lowest average diameter, while ALK 0159 is a little bit larger, and DOPE, as we saw in previous experiments, has a much larger average diameter. If we eliminate that DOPE from our DOE and check out the different buffer conditions, we can see that sucrose at 5% and 10% shows the best stability when freezing your samples down to -20 degrees Celsius, with a 0 degrees the average diameter below 100 nanometers. So outperforming even our standard PBS and tris buffers, which is great. It's our cryoprotectant of choice, and that's what we like to use. So that's how across Sunshine and Stunner we're able to elevate LNP production. On Sunshine, we were able to evaluate TFR, lipid formulations, and buffer conditions, as well as storage conditions for those lipid and buffer conditions. All this testing that we did in these experiments, which is over 75 samples, was done with 1 microfluidic mixer on an LNP platform that's able to scale from screening to production. Our experiments showed the benefit of using the right DLS tool for the right job. For larger particles where aggregation can strike, you do need to see information from lots of angles to really see what's going on with your sample. And all the data gathered in 4 different Stunner experiments took less than 3 plates. Loading each plate took maybe 30 minutes. So 75 samples in total. Each of those done in triplicate took about 90 minutes of total prep, while Stunner did all the rest of the data collection. And overall, combining these 2 instruments, we were able to evaluate sucrose as the best buffer as a cryoprotectant, and found that single-angle backscatter DLS can easily miss aggregation in poor samples, especially after storage. So, like me and the ladders, if you trust and rely on the right tools, you can optimize your LNPs and get to some pretty cool new heights. Thank you for attending this talk. If you want to learn more about anything you saw here today, don't hesitate to reach out to us at info@unchainedlabs.com, simply through the website, or right now, I'll be happy to take any questions you might have.
Thank you, Kevin, for a great presentation. I would now like to invite you to join me on camera so we can start our Q&A. Great. Our first question is, how long does an experiment take on Stunner?
So if you're running just the UV-vis part of it, just to take a look at RNA concentration, that takes about 10 minutes, 10 or 12 minutes. If you add on single angle DLS, you'll be done in about an hour for a full plate. And if you're running the full-on rattles to look at every angle of DLS, that'll take about 2 hours, 15 minutes for a full plate. So 96 samples.
Thank you so much. Our next question is, can you use the UV-Vis part of Stunner as part of an encapsulation efficiency assay?
Yes. So the UV-Vis part of Stunner, when it's reading RNA LNPs, is giving you essentially total RNA concentration. It's the same information you get on the sort of surfactant or Triton X arm of an encapsulation efficiency assay. So all you would do is replace that surfactant part of the assay with a Stunner read, do the free RNA encapsulation assay with RiboGreen like you normally would. And the whole thing ends up running about twice as fast with twice the number of samples, half the time, and half the dye standards and reagents. So overall, it's a big step up in efficiency, and it's one that we have application notes on that particular workflow that you can reach out to us and we'll share those details.
Thanks so much for that, Kevin. Our next question is, would this work for LNPs decorated with targeting proteins?
Yeah, so that's an interesting topic since I think a lot of LNPs nowadays are looking at targeting their delivery. But yeah, so Stunner's unmix engine that's looking at figuring out how much RNA is present in a sample can also look at the total amount of, say, RNA and protein that's present in the sample. So that way you can get a concentration, of the bulk amount of RNA and protein whenever you're, reading these little 2 microliter samples on Stunner.
Our next audience question is, what concentration ranges of encapsulated RNA can be prepared by Sunshine?
So that's a little bit up to the user. I'll say that Sunshine can run a flow rate ratio between 1:1 up to 1:10. And from there, it's just what your formulation can hold, what's the concentrations that you can get your RNA up to and get your lipids up to. I know that for most of this presentation, our typical ranges were between 50 and 100 microgram per mil with encapsulation efficiency results greater than 95%. And beyond that, it's kind of up to the design and performance of your lipids.
Great. Our next question is, can you use this in a GMP environment?
So Stunner, on the analytical side of things, has 21 CFR Part 11 software tools. It's right, has the kind of IQ/OQ tests that it needs to get into a GMP environment. On the LNP production side of things, Sunshine is designed to help you optimize your process, and then you take all those process parameters, you take those microfluidic chips, you translate that to the next step up, the Sunbather platform, and that's ready for GMP LNP production.
That would be super helpful. Thank you. Our next question is, what other sample types can Stunner test?
Yeah, so we talked about RNA LNPs and protein conjugated RNA LNPs. It can run just plain proteins. If you want to check out antibodies or Fabs or peptides or anything like that, you can get concentration and sizing there. Same thing for nucleic acids, same thing for viral particles. So it's really got a lot of applications that are very flexible to cover a lot of different use cases in lab. So imagine you're running, your IVT reaction before making an RNA LNP. You could check out your plasmid DNA concentration. You could check out your RNA, and then check out your RNA LNP after the whole thing's been put together.
Great. Thank you so much, Kevin. Our next question is, what is the minimum mass of RNA that can be used with Sunshine?
Okay. So I always think in terms of concentrations too and volumes. So I will say that the minimum volume for Sunshine is going to be depending on the flow rate ratio as well. So it's the kind of question where if you talk to us, we'll get more into the details. But let's say at a typical 3:1 flow rate ratio, the minimum sample volume is going to be about 1 milliliter. And then we have other platforms like Sunscreen that could do a little bit lower sample volume. But that sweet spot for Sunshine where it's producing that nice amount of volume that allows you to test, further experiments. That's what Sunshine's really designed for.
Well, thank you so much, Kevin, for answering those questions. Unfortunately, that is all we have time for today. Any questions we didn't get to, we will reply to by email. The webinar will be available on demand tomorrow, so look out for an email from us with the link. We'd also like to invite you to take a short survey to provide us with feedback on today's webinar, the link to which can be found in the Resources tab on the right-hand side of the screen or in the on-demand email. All that's left is to thank Kevin once more for a great presentation, and thank you to the audience for listening. We hope you'll join us again soon.
Thank you much.